An X-ray halo nearly 250,000 miles across, observed for 17 hours, placed 3I Atlas in an unprecedented category. No known interstellar object had ever shown anything like it. The detection survived rigorous verification and raised the central question: what kind of visitor can produce X-ray glow on this scale while crossing the solar system? Although NASA classifies it as a comet, the full dataset, involving morphology, composition, dynamics, and now X-rays, suggests an object that is increasingly difficult to explain with that label alone. To obtain the first X-ray portrait of an interstellar object, the XRISM mission observed 3I Atlas between November 26 and 28, 2025, performing 14 precise adjustments to keep the target in focus as it moved across the sky. The soft X-ray imager captured extremely faint emissions, but before confirming the signal, the team eliminated cosmic noise, scattered sunlight, and the Milky Way's background emission, testing every possible source of error. The result was unequivocal. A diffuse glow emerged from the nucleus and survived all JAXA verification steps, which ruled out instrumental artifacts and solar wind contamination. The detection became an open reference for reanalysis. The signal is real. The mechanism producing it is still unknown. For decades, solar system comets have displayed X-ray emissions, but this has always been a relatively contained phenomenon linked to active comas interacting with the solar wind. With 3I Atlas, something entirely new appears: a ghostly X-ray mantle extending hundreds of thousands of miles beyond the nucleus in an object that came from outside. And this matters because the historical record is clear. Oumuamua, the first interstellar visitor, showed no X-ray activity at all. Not a single photon above background. Borisov, the second, looked like a classic comet in many ways, yet still failed to register X-ray counts even under deep observations. The archive remained empty. For 3I Atlas to break this sequence, with 17 hours of observation and multiple background checks, the question shifts from curious to what changed here? The most likely explanation for this glow involves charge exchange. Solar wind ions collide with neutral gas around the comet, strip electrons, and release energy as X-rays. It is a known process, almost mundane, in the context of active comets. But the scale of 3I Atlas suggests an enormous gas cloud, far larger than anything seen in Oumuamua or Borisov. And if the cloud is that large, then either the object is releasing material in a way we are not used to seeing in interstellar visitors, or we are looking at a physical regime different from what we assume when we say, just a comet. While XRISM recorded the halo, Hubble was building a different kind of dossier: the shape, evolution, and geometry of the coma. Hubble's first look came in July 2025, just weeks after discovery. The images revealed a classic cometary coma, but with a striking difference. Instead of the expected rounded symmetrical glow, the coma stretched into a teardrop shape, with the tail extended along the object's trajectory. Over the following months, as the comet approached the Sun, Hubble mapped a dramatic transformation. The coma elongated and narrowed, the head brightened, and the tail began to trace an arc with persistent structure, as if sculpted by an invisible wind. Each new frame told a story of change. The leading edge became sharper, while trailing material appeared to split into ripples and filaments suggesting turbulent flows. In some exposures, faint striations hinted at jets or localized eruptions, yet the overall pattern remained consistent. A body losing material intensely, but with a geometry that did not seem to follow the solar system comet playbook. Then came the paradox that scrambles intuition. Compositionally, other instruments indicated an unusually low water budget. How can something dry look so active? That is where James Webb entered as a chemical interrogator. When the infrared spectrograph locked onto 3I Atlas, the numbers arrived with a clear message. The spectrum was dominated by carbon dioxide, accounting for 87% of measured volatiles. Carbon monoxide added another 9%, and water barely appeared at about 4%. For comparison, comets in our solar system typically have water as the main component, often above 70%. Here, the balance was inverted. As if that were not enough, Webb identified metallic lines in the gas plume, and the proportions were unexpected. Nickel exceeded iron by a wide margin. Normally, iron dominates. This detail fueled more adventurous interpretations, and some observers pointed out that certain industrial alloys can have nickel-rich signatures. Most planetary scientists rightly urge caution with conclusions, but the raw fact remains: more nickel than iron, and a level of dryness that places 3I Atlas in a category of its own. Now tie that to the X-ray halo. X-ray emission likely depends on a vast neutral gas cloud, yet water, usually the primary gas supplier in comets, appears suppressed. So what is feeding the coma and sustaining the spectacle? One hypothesis is that carbon dioxide, being volatile, could drive different dynamics. Jets and gas release more efficiently under certain conditions, even with little water. Another possibility is that the object's interior has been processed in ways that do not match solar system comet models, perhaps due to a different thermal history, formation in another region of another system, or heating cycles that altered the crust and release patterns. As if morphology and chemistry were not enough, the orbital problem emerged. Analysts at the Jet Propulsion Laboratory tracked 3I Atlas by comparing its trajectory with purely gravitational predictions. The numbers began to diverge. As the comet approached the Sun in late October 2025, observed positions started drifting from model predictions. The estimated maximum deviation was on the order of 9 × 10⁸ astronomical units per day squared, roughly centimeters per second squared, sustained for weeks. This is not impression. It is the fit of hundreds of observations from different observatories into a single orbital solution. Non-gravitational acceleration is normal in comets. Sublimation acts like a thruster pushing the nucleus. But in the case of 3I Atlas, the magnitude and behavior sparked debate. If the acceleration really is that large, some calculations suggest the object would have to lose a huge fraction of its mass quickly. That should leave dramatic signatures across multiple wavelengths. The observed activity is intense, yes, but debate continues over whether it balances the books at the scale implied by the numbers. Then came observations in visible and solar light. Stereo and SOHO tracked the comet as it intensified toward the Sun. Initially, it had the reddish tone typical of dusty comets, but upon reaching perihelion, the color story flipped. The red disappeared and was replaced by a bluish glow, bluer than the Sun itself. This is not something comets do often. Normally, they become redder near the Sun, because dust tends to scatter light in ways that favor that appearance. Here, the trend reversed, and cross-checks confirmed it was not a camera artifact. Brightness also behaved in an unsettling way. A meteorological satellite monitoring the space environment recorded 3I Atlas at unusually high magnitude for an interstellar visitor, especially one with a water-poor coma. The brightness peak tracked the color inversion, as if a new mechanism had entered the scene. Polarization measurements added another layer, the most negative value ever measured for a comet. Polarization is an indirect clue about the size, structure, and composition of dust grains. When a comet breaks records there, it sends a message. The dust is not behaving as usual. Behind all of this lies the human side, the pace of science versus the pace of the internet. Space missions and scientific teams follow verification and review protocols. This prevents errors, but slows public updates. Meanwhile, the information vacuum becomes fertile ground for speculation. That is why, on November 19, 2025, NASA held a press conference and reinforced the message. Nothing to worry about. Natural behavior. Comet physics explaining the dataset. The Pentagon, via ARO, also clarified the object was not a national security concern. The official narrative aimed to close the subject. But a story does not end when someone says, "There is no mystery." It ends when the data are fully explained. And here, loose ends remain. The debate gained extra fuel when a statistically improbable orbital alignment with Jupiter's Hill sphere was noticed, the invisible boundary where the planet's gravity can dominate. The calculated minimum approach fell extremely close to that boundary, with a difference smaller than Jupiter's own diameter. Some see this as inevitable coincidence in a universe of probabilities. Others see a detail worth attention because the pattern looks too good to be random. And as if that were not enough, in December 2025, ground-based images revealed structures more organized than the typical cometary haze. Narrow spiral jets, as if the nucleus were a rotating sprinkler launching material in coils. Spiral jets exist in solar system comets, but seeing them clearly in an interstellar visitor, especially with this chemical signature, adds another piece that does not fit easily. The presence of two tails, one dominated by dust and another by gas, reinforces the idea of distinct active regions, perhaps fissures or localized sources consistently releasing material as the nucleus rotates. Now 3I Atlas heads toward Jupiter's boundary, and observatories are preparing. What happens near that region matters because Jupiter is a giant that distorts trajectories and reveals the sensitivity of motion to small forces. If the path changes unexpectedly, if fragmentation occurs, if activity surges or collapses abruptly, it will feed models and debates. If nothing happens, the accumulated data will still be enormously valuable, because this object may be our best sample of how diverse the interstellar zoo truly is. And here is the strongest point. Every interstellar visitor is a time capsule from another planetary system. Oumuamua showed they exist. Borisov showed some look like normal comets. 3I Atlas suggests the diversity may be far greater, and that our models, based mainly on comets formed in our own cosmic neighborhood, may be incomplete. If CO2-rich objects are common out there, that reshapes our view of volatile distribution and even how other systems store water and carbon in their small bodies. This is not an academic detail. It is a clue about planetary chemistry on a galactic scale. If you enjoyed this story, leave a like, subscribe to the channel, and tell me in the comments what you see in these data. Are we looking at an extraordinarily unusual comet, or an interstellar mystery we still do not fully understand?